Welcome again, everyone. Thank you for joining us. My name is Karim Al-Masloud. I'm the Manager of International Projects at Premier Corex. I'm hosting this session. Um, Last session, we had Frank Zamora talk about rheology degradation uncovered. It was a great session, and I think this session will be great as well. If you have joined us before, thank you for joining. You know the rules. If you are joining us for the first time, it's good to see you. Thank you for joining us. Okay, today we are going to have the pleasure of attending the session with Sean Parker, talking about fracture conductivity evolution under shear conditions and chemically realistic conditions. Okay, thank you very much. Okay. Um, just a quick housekeeping rules. Please use the Q&A section for all your questions. Okay, we will answer all questions at the end of the session. The webinar is about 45 minutes, and we'll allow some time for questions at the end. The session is being recorded. You will receive a link for a copy of the recording at the end. Okay, and all attendees are muted. So if you have any questions or anything, please just put them on the Q&A section. Okay. Just a little bit about Sean. Sean joined Premier Corex as an energy industry professional. He's more than 15 years experience. Okay, he specialized in fracking, hydraulic fracking, well completions, optimization, oil field chemistry, pressure pumping, and fluid system designs. Sean has previous roles with Select Chemistry, ProFrac Services, FTS, and Baker Hughes. Okay, he has great experience, and we're lucky to have him today. Sean, it's all yours. Okay, please take it on. Thank you.
Thank you, Kareem. Hi again, Sean Parker. What I would like to do is, this is more of a continuation from what Frank Zamora had presented at the last webinar, primarily with perforation shear and what is occurring with the fluids and proppant as they pass through there, and then how are we going to correlate that back into fracture conductivity? As many of you know, we can't negate fracture conductivity. I know it's been a topic of discussion since the 1960s and even before, but it is it's the ultimate go-to as to what we're going to get in terms of deliverables from the well. It's our foundation for fluid selection, proppant. My thing, and we'll see, is that it's historically been a static endpoint. We're using a set, it's more of a static property as opposed to dynamic, and we'll get into it as to why I think that should change. But our wells, we're dealing with fracture, complex fracture networks. The conductivity is controlling those early time rates, drawdown responses, and more importantly, this long-term decline behavior, which kind of goes back into the shear rheology that we'll be talking about. In terms of the formula itself, it's just the product of permeability times the fracture width. I won't get into much on the half length. That's the ultimate control, what we're going to get in terms of recovery of hydrocarbons, but these are all still very, very important facets for how we complete as well as design our wells. So a little bit of history, and this is always fun. Again, in the 1960s, they had RP61 to an API standard. This morphed into 56, RP56. And this was really nothing more than two steel plates or pistons that were compressing against proppant. If you were to be an outsider and look at this, you would determine that these were very simplistic. The people that created these realized they were simplistic. They were simply looking for comparability and repeatability. My standpoint is that the problem isn't the testing methodologies themselves. It's that the formations that we are treating have evolved and changed so much faster than the testing methods. When we first started doing these were based upon gels. just natural polysaccharides, lower pump rates, significantly lower, and the proppant placement was very simple. Although we didn't make it simple, it was, compared to what we see now, it was much simpler. The Cook cell lineage, while it was appropriate from its time, I think we've changed dramatically enough that this needs to be revisited. And I will say this, in the course of looking into this and from my previous experience, when we went from 56 to RP19D, which was in the late 1990s, early 2000s, much of what I'm going over, or the concept for change, this was almost a bit of deja vu, because the same principles were being presented, in that what we're doing in the lab is not what we're seeing in the field. We need more realistic testing methods. Those from Palish, Brannon, and some others, along with Montgomery and Smith. And there's numerous other papers that were presented for this type of change. And even then, it slowly evolved. We had 19D, and then the long-term, the ISO 13503-5, up to now, where we're doing another revised 19D. But still, even with the latest revision that I believe was in 2023, it's my standpoint that we're not up to par. We're not up to par because of this shear rheology. And I didn't mention it, but if you have the opportunity to go back to at Premier Corex webinars on YouTube and view that, Frank Zamora goes much more in depth on what's really happening once the fluid goes past those perforations. So on the standardization, I'm not advocating for a complete change as opposed to an evolution of these. These are still essential for creating baselines. And I know people can get passionate about these standards as to what should or should not be done. It's been, again, since metaphorically the dawn of time, people have been arguing over this. So I'm not looking to be a huge disruptor, as opposed to create something that's more modified to today's standards. When we take one of these current API testing qualifications or standards and are just using some base proppants, we have, I would say, artificially high conductivity levels. When you start adding in non-Darcy flow, damage, formation fines, cyclic stressing in particular, that conductivity gets down to effectively zero. And now we're adding in this shear degradation to the fluids and proppant, which it's just, you can't get much worse. So not to say that we don't need these standards. Again, we still need these baselines, but it's critical that we evaluate these things correctly so we have a better understanding of what actually is happening to our conductivity once we've completed a well. Specifically, and from our testing standards, this is all relative to polyacrylamide-based friction reducers, but it can easily and readily translate into linear gels and cross-linked fluids as well. But those remain to be tested from our standpoint. But again, with these standardizations, there were big wins, because it then enabled people to qualify different proppants and fluid systems, and you had some mode of repeatability and design consistency. Certainly, if you've ever set one of these up, you realize how difficult it is to maintain equilibrium, not just on a single unit, but let alone trying multiple units. And invariably, you're going to have a difference in results. And it's not so much, it's just in setting it up. It's a very delicate setup. But we do what we can, and it's still giving us decent results. But all of these still are assuming that our fluids are, I have it labeled here as pristine, for lack of a better word, but I would say undamaged. The fracture faces, we're still using the Berea sandstones in most cases. Sometimes we'll actually use shales. But more often than not, it is that smooth surface and a relatively short exposure time that we're not really capturing what is occurring downhole. So there's these major gaps. Let me pull up this. 2 and 3 we've known about for a long time, and we deal with them. We deal with them with these modified cells and have created tests outside of 19D to help show or bring some realism, physical realism to what's occurring downhole. But we haven't really addressed this shear history, and that's mainly because it's so new, relatively newly discovered. So this, again, is my focus and one of the critical aspects that needs to be addressed, not just in how we're going to treat it in terms of fluid systems and or proppant, but the conductivity as well. All of these, this 1, 2, the new one included, I don't consider them gaps. As I mentioned, we needed baselines. And the people that created 56, 61 certainly weren't, not aware that there were limitations to what they were seeing in the field, but they needed those trade-offs to establish these baselines. And again, we still need to keep them. So our reality now is we've had knowledge of shear of fluid and some potential proppant damage through the surface equipment, whether it be the pumps, the fracturing pumps, and or the blender, but those are to a lesser extent. Wellbore, same thing. We historically, with slick water or friction reducer type fluid systems, we're testing at 511 reciprocal seconds, and that has been and still is adequate to account for any shear of the fluid system that's going through the wellbore. And as you know, as our wellbores are getting longer and longer, our laterals, and of course the water itself is our using produced waters with more divalence. It's even harsher on the degradation of the polyacrylamide. That testing is still significant and at the forefront just for getting something through the wellbore. The problem comes in, as I mentioned, with these perforations. This is where we're going from testing at 511 reciprocal seconds to where thus far from the peer group and their field testing, we're seeing shear rates of up to 250,000 reciprocal seconds. So you have an exponential shift in what the fluid is doing down along the lateral here. As it's going through these perforations, we're not pushing through what we thought. So all the testing we're doing is certainly relative to what's in the lateral here, but once it's past the perforations, it's no longer relevant at all. You have a serious degradation to the fluids, to the polyacrylamide, and proppant damage as well, which we'll get into in just a bit. So one other aspect I want to cover is on regained permeability. We often hear, what's the regained perm, almost as a buzzword, but I don't consider this to be a useless test. I think where we are now, it's just not complete, as opposed to using the phrase retained permeability. Whereas, regained, historically, we're considering that the damage is reversible and chemistry is secondary. Can flow be reestablished is what permeability or regained permeability is answering, as opposed to what conductivity is retained. And it's not necessarily a play on words. There is a tremendous difference between those because, these irreversible damages that are occurring, whether it's formation fines, surface softening, we are fracturing and displacing fluids into chemically reactive formations, much more so than we were in the conventional sandstones. That and any residue that's being left behind, whether it's from guar or certainly polyacrylamide, you're going to be very hard pressed to displace that. So as I indicate here, liquid testing without context, it does become misleading. So this triangle here on the right, I actually kind of like this here. You have physical realism, which I would term as what we're seeing in the field. This is where academia comes in, colleges, as well as any type of bespoke testing. These are the more, well, historically, some of the rarefied modified cell tests that are occurring. And you get excellent insights and scalability. Does need improvement, but this is trying to get down and knit to the nitty gritty, if you will. Repeatability and the comparability, these, in fact, are more of the where the API standards come in and the ISO. And again, this is where baselines are established. The throughput and cost, this is more of the commercial side with enhanced APIs. And these historically are bridged practicality with field relevance. Now, I'll state that if anyone tells you I can give you all three of these, that more often than not, you're getting or hearing marketing hype. You can pick two, but you can't have three as it stands now. Where I'm looking at is trying to get us to where we're still working off of these API standards, but bridging that gap towards the physical realism. And this is more about sequencing. Again, we're not replacing, but sequencing from this repeatability and comparability and adding in this physical realism. And I'll get more into that here in just a second. So speaking of academics, one paper that I came across was from Jesse Guerra in 2019. And again, there's a considerable number of insights from both commercial or professional publications as well as academic. But this particular work represents, it's more of a systematically validated effort to take those API baselines and bridge that gap towards realism while you're still preserving those standards, which I do find critical. One of the bigger aspects that I do like is the use of N2. Using nitrogen affords this faster stabilization and creating these baselines. And then we can couple this with the damage mode, where we're bringing in these fluids as well as proppants that have undergone ultra-high shear damage. And then on the data utilization side, rather than maintaining a static endpoint, we can use these exponential decline functions and create a workflow. And this is where we can start to develop, with enough data, predict initial conductivities for other loadings. And this is going to be critical in our research for the Frac Consortium, as defining what the limits are relative to proppant loadings, proppant types, as well as fluid systems, what works and at what loading. And of course, these can be applied over different stress ranges as well. So, from a laboratory perspective, we're again looking at some of these static endpoints, but from an engineering perspective, we don't design wells on static endpoints, so why test that way? We're masking rates of loss, the sensitivity to stress, and more importantly, right now, from my vantage point, that sensitivity to chemistry. If in this instance, if we're tying this decision rather than making it just simple lab theory, I think we'd get a lot more buy-in from the industry overall. And again, these trends rates better inform rather than just absolute values. You can make a more keyed decision. So right here on the right, within this simple bar graph, this is from the Peer Consortium, where they did some field testing with proppant, specifically 4070 local sand. And that which is in the blue was the initial mass fraction over the sieve mesh size. And it was a true 4070. The orange represents that same proppant after it went through the perforations. And the base fluid system was, initially a 3 to 4, call it 1 gallon per thousand of FR, or 3 to 4 centipoise of viscosity. But you can see that at that instance, we went from a 40-70 more so into 100-120 mesh. And not shown is what was in the cup. And I suspect if they had sieved the cup, you'd be more into a 100-200 mesh proppant. So there's a considerable difference there between thinking I'm putting 40-70 into my formation when in fact you're effectively putting in dust. And that's a considerable difference. So if our fluids are shear conditioned and the chemistry is altering these fracture faces, then again, this testing wherein we're looking at clean, short duration tests miss the dominant mechanisms. And again, that's something that we've known before, but knowing what we know now with the shear history, as these fluids and proppants are undergoing through the perforations, that's kind of a game changer in my book. So I don't think we have to make this more costly. It's just more targeted as to how we're doing our testing. And particularly when going back to the use of N2, this is more about efficiency rather than academic perfection. That's always going to be there. Something needs to work on. Somebody needs to achieve their doctorate. They can continue to work on that. But given the level of proppants and fluids that need to be tested from the Frac Consortium perspective, we need some type of repeatability, but be efficient in the ability to expedite this. So again, on the Frac Consortium aspect, really want to keep these API ISO standards as baselines, add realism where it matters, focus on consistency and turnaround, and in addition to try to remove any ambiguity to it, and make this an evolution, not just static endpoints, or completely change what we have been doing. What we have been doing is good. I just believe we can do better. It's not a one lab, one result scenario. That's certainly important. In that way, there's less bias, I should say. And we're not a standards body. We're not a field simulator. That's going to be left up to the peer consortium that's actually performing the field tests. We're just looking to collect the data, give it to them so they can generate some reasonable decisions as to what's actually occurring downhole. So for the industry itself, this is going to give a better differentiation between what looks on these API tests, these baselines, but behave considerably different under shear and its associated chemistry. We will be able to get more defensible decisions in our completion designs and better risk awareness. And I realize that cost matters, but ultimately operators do care about avoiding surprises. And if we're not understanding the full scope, if we're not understanding just the reservoir, but the completion design itself, that's ultimately going to lead to higher costs. You simply can't get around that. And this differentiation will give you fewer surprises. And obviously suppliers are going to benefit because they're not innovating something that the industry doesn't need, and they're not going to be punished by oversimplified tests. And I feel that this is how things are going to evolve from evidence, not just simple opinion, because as we know, everyone has one. So from a closing thought perspective, this measured evolution, let's not make conductivity static, but more of a exponential trend. Let testing evolve with the completions rather than hold it back. And the current testing protocols and completion designs reflect pre-perforation. We need to start looking at what's occurring after it occurs, after it passes through the perforation. With that, I do appreciate your time. Any questions you may have, I'm happy to answer them.
Thank you. Thank you very much, Sean. That was quite interesting. Having not been quite familiar with that, I've learned something today. So thank you for that. Appreciate it. Okay. So we're a little bit ahead of schedule, I think. We have about 35 participants. Thank you all for joining. However, please, obviously the room is now open for any questions. If you have any questions, please post them in the Q&A section. If you can't think of a question right now and want to think of one later, please don't hesitate to email us, and then we will make sure that we will respond back with answer to your questions. Okay. Okay, right. So if we're done. I think we don't have any questions coming in from the audience right now. Let me just check the chat and make sure that nobody's asked questions in the chat box, actually. So we do actually have a comment and a question. So 30 years ago, when we were developing long-term proppant testing procedures, it was found that silica saturation of the flowing brine made a big difference in the performance of some proppants. Silica saturation made sense at the time since we were mostly fracking sandstone formations. But is silica saturation really the correct baseline for today's myriad of reservoir rocks? Sort of doubted, which means the baseline data understood for some proppant is incomplete.
Yeah, no,
comment on that, Sean?
Yeah, no, I mean, that's just spot on. There's a considerable number of tests that still need to be, performed upon these newer shales in particular. Again, because they're so chemically reactive. It's relying on historical data that certainly bears no relevance to the rock that you're fracturing seems to be counterintuitive, but here we are.
Okay. All right. Okay. Thank you. Okay. So we do have another question. So how do you test 25 thousandths per second?
So 250,000 reciprocal seconds.
Yeah.
That's a big number. So what we have created here at Premier Corex is a test cell where we're displacing 1 liter of fluid. And that's going to be, a fluid of your choosing, so to speak. Right now we're doing polyacrylamide-based FRs, but we're displacing it with nitrogen through an 1/8 inch orifice, or whatever orifice that we're calculating from. But we're using the displacement time for the nitrogen from start to end that we're filming, and we are in fact able to capture that. And it is a very dynamic, as you would imagine, at 250,000 reciprocal seconds, it's roughly 1 second to displace 1 liter of fluid. So if you can imagine that, that's fast. And the output, this again was started from what the Peer Consortium did when they were collecting fluid samples and had that, oh, wow, because it was just completely visible when they were collecting it, that the fluid that they were retrieving was in no way what they were putting downhole initially, or through the tubulars, I should say. And then, of course, the viscosity checks at that point confirm that. So, one of the bigger things comes into how do we mitigate that? Is it just more loading of FR? That certainly may help, but then we're going to have to look at the balance, and this is where conductivity comes in. Are we going to create more damage to the reservoir by introducing more broken fluids, or in this case, broken polyacrylamide? So what is that balance? And that's kind of one of the things that's also part of our investigation.
Okay, thank you. So we do have more questions now. So Sean, thanks for the presentation. May I ask if you would propose lower or higher mesh for proppants considering shear forces along perfs?
So very good question. That's almost in line with do we pump more of a viscosified fluid, or do we increase the number of perforations at albeit at a smaller diameter, in order to maintain limited entry. And I would say right now everything's in up the air because Pier has tested different proppants from 100 mesh to 4070, and whether they're local, white sands, they're all performing differently. So we're still kind of in the dark on that, and more testing needs to be done. They've had their initial results. We've done some initial testing here at the lab, but it's certainly a good question. Do we pump more and hope for the best? But obviously, if you pump more, are we going to increase the risk of pumping more in a broken fluid and therefore bridging off or screening out sooner? If we pump less, there's the potential that we have less broken proppant, if you will, or sheared proppant. But are we going to go back to some of the earlier work where we're looking at more of a partial monolayer, which wouldn't be bad? As I sit here and mention that, I think to some extent the solution has already been presented to us. As many papers that have been written on this, it just may not have been as relevant as it is now. So while we're sitting here saying, what can we do differently? I've always found out that it's always good to go back and look historically to see what has been done, or in this case, what has been written, and can we apply it to now? There's lots of good papers from some very, very bright people that have been done over the past decades that, again, it may not have been relevant then, but it's more so now.
Okay. Thank you. So we got another comment here. It says also most of the baseline data was generated using 2 pounds per foot square of proppant loading. This is way above what we are placing in shale, and the shale is softer than the sandstone. Another reason why the database used today is incomplete for understanding conductivity in shale. You comment on that?
Yep. So that 2 pounds per foot. It's where do you target? Are we going to go to 1? I think these are things that we still have to ascertain as to what is manageable in terms of the proppant loading. What's the optimum loading? Is there one? Because that's going to change based upon your perforation schedule, the formation you're going into. I do not disagree that it's not germane to what we're seeing, but in terms of referencing that database, I would say, yeah, if you're looking at that, then you're already off the mark.
Okay. And then, but do we need a whole new type of fluid to deal with the shear? Another question.
Potentially. We're just starting out with this, again, looking at polyacrylamides. We are going to look at, we're going to go back and look at linear gels, cross-links, cross-link fluids. I do know that there are some alternative chemistries that are in the works from different chemical manufacturers. They may be the answer. Or it may come back down to coming full circle where we're back to looking at linear gels. One of the things that pops in my mind often with this is the transition from low loading cross-link fluids and low loading linear gels. I'm talking 15, 20, 25 pound fluid systems that were guar based. When we transitioned into friction reducers, our primary focus was on, can we achieve the friction reduction we need to obtain the designed pump rate to compensate for going to slick water? And then do we have the viscosity to achieve the desired proppant transport? Now, the manufacturers had said, don't look at viscosity, let's look at elasticity or G prime. And that worked. I always referred to it when you looked at the 3D models I always called it the magic carpet, that you could see the proppant just kind of floating along there, along those long polymer chains. However, that fluid certainly didn't undergo that type of shear. So I have to really question, do we have that elasticity? And from what we've seen, we don't have the viscosity. Therefore, we don't have the elasticity from our testing either. So maybe a new fluid system, modified, higher loading. Again, these are all things the consortium intends to find out.
Okay. Quite interesting. Okay. Thank you, Sean. Does anyone in the audience have any more questions? Okay. Well, thank you very much. If you think of any questions, Sean's contact details are right there. Oh, we have more. Okay. So in terms of propellant, how is the behavior of ceramics?
So yeah, we have not looked at ceramics yet, though that is top of our list, as are ultra lightweight proppants. That it's the shears certainly something to look at, as well as the ability to transport. And that's a great question because I know we already have a lot of some ultra lightweights as well as some very fine mesh ceramics that can offer some far-reaching proppant effect. So yeah, these are things that we have to test, and we can readily do here in the lab. So it's all part of our plan to test those.
Okay. So another one is, would there be consideration around higher crush strength proppant than 40, 70, 35T or 100 mesh to avoid proppant shearing? Would it make sense to introduce artificial proppant with higher crush strength?
Potentially, or does that higher crush strength, does it entail having it being more brittle? I mean, when this proppant is going through the perforations, it's physically being sheared or cleaved, if you will. So those proppants with very sharp angular edges, they're getting cleaved as they go through the perforations, and that's what's causing the reduction in size. So if you don't have the angularity of the proppant and the higher crush strength, it can maintain its initial size, then that's certainly something to look at. Now keep in mind, again, that cost factor is always there. So it's always going to be a tightrope. But all we can do is present the facts and let the end user make the decision for themselves. One thing that I've really taken to liking a phrase comes from Dante over at NSI. And he postured the question of, what if we've gotten really good at making really bad wells? And I think when you look at some of the ultimate recoveries on a trend, as we keep going longer in lateral length and perforation designs, that would hold true. I know we all say we're doing what we can, but when you look at the ultimate recovery on some of these wells, it's not impressive. It's not something you brag about. And I do know somewhat as an industry, we've become demoralized into simply relying upon what you would typically hear in the field, in that I have a successful completion because I got the dirt past the perfs. The irony is that's pretty much what you're doing right now. And I think we can do better.
Okay. Thank you, Sean. Okay. Great. I think that's the end of the questions. Thank you all. If you think of any other questions, Sean's contact details are right there on the screen. You can also contact us at sales@premiercorex.com for any questions, any future about this session or any future sessions or previous sessions. Okay. Thank you very much. Our next session is going to be on the 10th of March. Okay. The presenter is Abhijit Mitra, who's our rock mechanics specialist. Abhijit's topic is going to be linkage between composition and mechanics properties of rock, a Permian Basin example. Okay, that is going to be a very interesting session. Thank you very much for joining us today. Please go on our LinkedIn page, follow the page for any updates about our webinars, and we'll hope to see you back in 4 weeks with the next session. Thank you all, and thank you, Sean, very much.
Thank you, everyone, for your time.
Thank you.